So we're going to be looking at gravitational fields. So we're going to be revising this full chapter. I'll try my best to cover everything in this video, whatever I can. But I will obviously miss out a few things that will be very in detail that you might get from your lectures or recordings or from your teacher when he explains you in class. And so this is just for revision, just to refresh the main things, the key points. But for deeper understanding of the chapter, obviously you have to go through the chapter by yourself and personally do the question and all of that. But this is a good video to help you revise and get those key points that come in exam, right? So here I have the objectives, okay, which is going to be going straight forward into them. So first of all, let's try to understand what is gravitational field, right? So you should already know what is gravitational field. So dear student, gravitational field, we're looking at gravitational fields. So gravitational fields are basically always attractive. That's the first thing you have to understand. So they're always going to be acting towards the mass, okay? So there's a thing that I like to always say, that mass attracts mass, right? So it's always attractive. So whenever they give you an exam, planets, or sometimes they might even give you something called as a point mass as well, right? So they might give you a point mass, okay? Point mass. So whenever you want to draw the field lines, you want to draw them in this way, the same way you draw the electric field lines, but it's always attractive, okay? So it's always towards the object. So if I put a test mass here, test mass, it will always be attractive, okay? So it will always be attracted. And notice something, a smaller mass has less field lines. So less field lines for a smaller mass, and there is less density as well, because there's more space between the field lines. And for a bigger mass, we have the space is more dense and there are more field lines. So you can make a comparison like this as well. Okay, so you can maybe get a 2-3 mark question on this as well, and there has been questions on this, okay? So you just need to keep that in mind. Okay, now we're going to be talking about some formulas that you have seen. So first is the gravitational field formula, which is basically force exerted on per unit mass. So force on a unit mass, and this is specifically gravitational force. Gravitational force on per unit mass is gravitational field, and it's a vector quantity, very important vector, and the units for this are going to be Newton per kg. Okay, then if we have two mass M1 and M2, and they both are going to be exerting an attractive force, so it should actually be this way. The arrow is a bit wrong. It should be this way. So they both will be exerting an attractive force on each other. So the attractive force is basically going to be equals to G M1 M2 over R squared. This is Newton's law of gravitation, okay? And remember, this is also a vector quantity, okay? And remember, we can combine these formulas to get a final formula for the gravitational field, which will be equals to G is equals to Gm over R squared. Okay, so remember this formula as well, very, very important formula. Okay, one very important thing, what mass is this one, right? So let's say this is M1 and this is M2. So let's see M1 first. Okay, M1 is going to be exerting a force on M2. Okay, so the gravitational field of M1 is equals to the force on M2, force per unit mass, and that unit mass is M2 actually. Okay, and then when I plug in the formula, Gm1 M2 over R squared over M2, M2 gets cancelled out. So I like to say this is the source mass, okay? And it will be really easy to tell in exam. They will give you that the gravitational field of this object and that object and so forth. Okay, so there's a quick revision on this. Okay, you have to be very familiar with these formula. All right, now we're going to be drawing the gravitational field lines for this mass. Okay, so let me just draw this. So we're going to be having gravitational field lines right over here, and so the relation between gravitational field lines and the distance. So we have the distance r here and gravitational field line g here. Okay. So our relation, we know G is equals to Gm over R squared. So it follows a inverse square relationship. Okay, inverse square relationship. So if it's R initially, then G is just going to be G. If it's 2R, then G will decrease by 4 times. And if it's 3R, then G will decrease by 9 times. So if I look at it from here, then G should go like this. Right? Let's go like this, okay? And inside it's going to be like this. If I go inside the mass, then it's going to be like a straight line, and then from the surface, okay, this is the surface, this is the radius of the star or the sphere, and then from the sphere's surface, it's going to be maximum, and then it's going to go down as you go away from the sphere or star or planet, okay, whatever you want to say that, okay? Now, in this way, in the other direction, so let's say this is positive, this is negative. So in this direction, the negative direction, you're going to have the gravitational field being in this direction, okay? Because what's going to be happening? This is going to be moving like this. This is going to be moving like this, right? So it should actually be the other way around. Let's just move it there. This should be like this. And this should actually be like this, okay? Alright, so that's how it is, okay? The direction of gravitational field is opposite, so that's why I switched the signs, okay? So remember, it's a vector quantity, so both sides should be different directions. Looking at the comparison between gravitational field and electric fields. So remember, gravitational field arises due to masses, and this arises due to charges. And remember that both are vector forces, so both have directions, but gravitational fields have attraction only, no repulsion, whereas electric fields have both attraction and repulsion. Okay? Now both of these are given by the formula G is equals to F over M and then E is equals to F over Q, very similar formula. And both the gravitational field and electric field obey the inverse square law. Very, very important. Okay? So there's some things you have to keep in mind. And then you can see the uniform gravitational field and uniform electric field formulas is very similar as well. And then you have the inverse square law, which we were just talking about. Okay, so we can just look at this as well. Right. Yeah. So we're going to be talking about electric potential as well. Okay, let's look at this. Okay, so this is the electric potential and the gravitational potential. So both potentials obey the inverse relationship, and the potentials are considered zero at infinity. Okay, and remember that the gravitational potential is always negative, but for the electric potential it can be positive or negative. Okay, so there's some things in mind now. I've actually taken the mark scheme for one of the 6 markers they asked on to compare and contrast between electric fields and the gravitational fields. So give me a second. Okay, so look at this. It's a very similar answer as well. When we look at that table above and we see this answer, it's very similar. But I have to explain a few points from here. Remember, gravitational fields always acts on mass. But the electric fields, the electric forces, they exert the force on mass. It's basically the definition. Gravitational field is basically gravitational force on mass, and electric field is electric force on mass. Okay? And then we talk about the second point, which is, which we just discussed actually, just saw it. You can talk about electric forces being always attractive or repulsive, and gravitational forces always being attractive. And then we just talked about the electric potential above, that gravitational potential is always negative, never positive. And electric potential can be positive or negative. Okay? So that's an important thing as well. Okay. Now, both fields have infinite range. So what's going to be happening is that, remember, we drew this graph above, right? Or let's just look at this graph. These graphs. Look, these graphs are basically decreasing, but remember, the graphs never touch zero. Okay, same with this. The field graph is decreasing, but it never becomes zero. It becomes so small that we can consider it zero. Okay, so these graphs, very far distances, the gravitational fields and the electric fields become so small that they're negligible. So they have an infinite range. So we can see that they're really, really far away. They still do exist, but very small. Okay, so keep that in mind. That's I've also drawn a graph here as well while I was teaching my class. So that's an important point. The second one you can go with is action at a distance. Basically, you know that when you touch things and you push people, you touch people and all of that, you're coming into contact with them and you're putting a force, right? But here, without coming into contact, the forces are being exerted. That's what action at a distance means. So you see, you have a positive charge and a negative charge. They're not in contact with each other, but they're still exerting a force on each other, right? A similar non-action at a distance is also magnets, right? Magnets, gravitational forces, electric forces, these are all action at a distance, force without contact. Okay, that's another very important point. And then one thing we discussed just now is both gravitational field around a point mass and a point charge obey inverse square law. Very, very important point. And the last point is a bit of a new point, is that you have to remember that the interaction between the charges is much more than the interaction between unit masses. This is because the charges have a much smaller mass, and if they have attraction or repulsion, that's going to be much greater. Okay, so these are some things you have to keep in mind, right? So just go through these, just look at these. Okay, you have to know these. They can ask it in 6 marks as well, but they mostly ask in MCQs or 2 markers. Okay, now we're going to be looking at 2 very important things. Those are I'm going back to electricity chapter, gravitational potential, and something that you might have already seen before or you've heard about is gravitational potential energy. Okay, so the gravitational potential is the energy required for the work done. Let's go with that one. The work done on a unit mass to bring it from infinity to that point in the field. This is the definition of gravitational potential. And then gravitational potential energy is work done on a mass to bring it from infinity to that point in the field. Okay, notice the difference. Work done, okay, everything is same, but we're talking about a unit mass and we're talking about a mass. There's a big difference between that. Okay, so you have to keep that in mind. Okay, so we're going to be looking at the gravitational potential, which is V is equals to minus Gm over R. And then we also should be familiar with the formula of GPE, which is equals to M times V. And the change in GPE, which is equals to M change in V. Okay? Alright, so remember that all of these quantities are scalar, so scalar quantities, okay? And I've just shown you the definitions as well of these. The reason that our gravitational potential is negative, okay, and even when you see the gravitational potential energies, they will also give you a negative answer because this value here will be negative. So if you plug it into your formula down here, then you'll also get the gravitational potential energies being negative as well. So the explanation for this is that gravitational fields are always attractive. So when you bring something from here to here, okay, or let's say from infinity, where R is infinity and the GPE is equals to 0. So what's going to happen is, you might be surprised, but this is the max value of the GPE. Okay, so when you bring something, so if we move the object from here to here, then what's going to happen is the object will be attracting, right, to the mass here. Okay, and because of that, it's gonna increase its speed, it's gonna gain motion, and it's gonna come closer and closer, and so it's gonna basically be gaining kinetic energy. So it's gonna be gaining kinetic energy, and it's gonna be losing something, and that is the potential energy. So the potential energy will always be changing into Ke. So it will always be going down, and it will always be changing into Ke. So it will always be a negative. Okay, and that's why we always have a negative sign, is because it just shows you that all of this potential energy actually got converted into kinetic energy. Okay, so that's what it shows, right? So you should be very familiar with these formulas and very comfortable to use these, because many students, they struggle to actually use these formula, right? Now I'm going to give you one quick situation that pops up a lot in exam, and they'll typically say that a satellite goes from let's say from A to B, okay, and you have to calculate the let's say from A here to B here. Okay, so we're going from A to B. Now what's going to happen? Since we're going away now, your potential energy actually is going to be going up, and your Ke is going to be going down. Okay, but the potential energy will still be negative. Okay, because remember, the maximum value of the potential energy is at infinity, and that is 0. Okay, so we're going from A to B, and I want to find the change in GPE going from A to B. Now that's going to be m, the mass that I'm moving from A to B in the position of the field, times the change in V. So at this point, so let's find the change in V. Change in V is the final potential minus the initial potential. So final potential is the potential at B minus the potential at A. Okay, and then let's say this is distance R2 and this is distance R1. So now what I'm going to do is I'm just going to plug in the values. So Gm over R2 minus, this is minus, by the way, minus sign, minus Gm over R1. Okay, so that's going to give me minus Gm over R1. Now minus minus becomes plus for R2 here, and plus Gm over R1. Okay, I think that's how it should be. Yeah, so this minus minus becomes plus, so Gm over R2 plus, okay, Gm over R2, remember this minus sign, plus Gm over R1. Okay, and then I'm going to take this entire value and I'm going to plug it in here, times the mass of the object I'm moving. That's pretty much all we have to do. And there are a lot of good questions on this that they like to ask, so just be prepared for these type of questions. Okay, now look at this very carefully. Okay, the gravitational potential is the work done per unit mass. Okay, so it's a property of space. It's a property of that point in space. So it's a work done per unit mass. Now, for an object of mass m, then the gravitational potential energy will be m times as large as as for an object of unit mass. Okay, so basically they're trying to say that the gravitational potential energy is the mass times the gravitational potential. Okay, and then it says for two isolated masses, so for two isolated point masses, m1 and m2, which are situated at a distance r in a vacuum, the gravitational potential energy is actually going to be G m1 m2 over r. So this is another formula, and you have to put the minus sign there as well. Okay, right, so that's all for this part. Okay, now we'll be actually going to something else. So we have seen the formula of GPE. GPE is equals to m, change in V, or if you have two isolated point masses, GPE will also be equals to GMM minus over R. Okay, but then what about this formula, GPE is equals to mg change in H? Well, there are two very simple reasons why we can't use this. It's because, first of all, this formula assumes that Earth, the gravitational potential at the surface of Earth, that the GPE at the surface of Earth is equal to 0. You know, we teach you in IGCSE and in even your AS level that when something is here, its GPE is 0. Okay, but actually there's nothing special about the surface of Earth that causes GPE to be 0. If you have objects moving in space, they will have a gravitational potential here, and when they come down, they will still have a gravitational potential. There's nothing special about this point. But there is something very special about a point called infinity, or very large distance. At that point, we can say that GPE is equals to 0. Okay, so for practical purposes, we can say that, okay, G is not GPE is not 0 on the surface of Earth, right? So because of that, we can't use this formula, okay? So that's the first reason. The second reason is even more important, is because G is not constant. As we're going to go up, we're going to go to a greater height, the gravitational field will become weaker, so the G value will go down, okay? That's the second reason behind it, right? Okay, so just keep this in mind. You can ask a few tricky questions on this as well. Not tricky, straightforward, so just keep these in mind. Alright, now we're going to be looking at gravitational fields and orbit, basically. So we're going to be looking at orbit, okay? Orbit of satellites, okay? So first of all, we have this object and it's kind of moving around. Now, this object, the centripetal force of this object is equals to the gravitational force. So the mv square over r is equals to gmm over r square. The m cancels out, and then we have v square is equals to gm over r, okay? And then v is equals to square root gm over r, okay? So that's some of the things you can do, and you can find the velocity through that, and then you can plug the velocity is equals to r omega. You can find omega, and then you can do omega is equals to 2 pi by t, or you can do omega is equals to 2 pi by f, and you can use all the formulas you have seen in circular motion, okay? So you can apply all these formulas because the object is moving in circular motion, okay? Right, so that's the first thing you have to keep in mind, okay? We'll discuss a little bit more about this, okay? Or actually, I think I should discuss it right now itself, okay? And that is going to be Kepler's, so first look at this, and then I'm going to talk about the next thing, okay? Okay, clear with this? Now we're going to be looking at Kepler's third, give me a second, Kepler's law of planetary motion. It's kind of similar. I'm going to be saying that the centripetal force is equals to the gravitational force. They ask you to prove this, by the way. And then the centripetal force, I'm going to write m r omega square. And then I'm going to write gmm over r square. Cancel this out. Take the r down. You get omega square is equals to gm by r cubed. And then omega is 4 pi square by t square. Gm over r square. And then I'm going to make t the subject. So I'm going to say t square is equals to gm 4 give me a second, 4 pi square r cube over gm, okay? And then I'm going to square root both sides, and I'm going to get t is equals to 4 square root 4 pi square r cube gm, okay? And the Kepler's law actually stops right over here. This is actually Kepler's law. You can remove the square root. So Kepler's law actually says that the time period square is directly proportional to r cubed, okay? Where r is the radius of the orbit. Okay, so that's one thing you have to keep in mind as well. Very, very important, this concept. Okay, now we're going to be talking about, I have the same slide, so we're going to be going over the same thing again, just same concept, but just we're going to be talking about the escape velocity, okay? Very important point. Remember, the potential energy and the gravitational potential energy and the kinetic energy are two types of energies that we have. So we have Ke and we have GPE, okay? So when we have Ke being equals to GPE, okay? Ke is equals to GPE. At that point, the object has a velocity called the escape velocity, okay? So we have GPE that's going to be acting. So we're going to have GPE acting on this object. The gravitational potential energy in one direction and the Ke in the other direction. When both of them are equal, at that point the velocity is the escape velocity. So we're going to have mv square over gmm over mv, okay? Gravitational potential. Write it like this in exam. mv square over minus gmm over r. I'm going to ignore that minus sign, okay? Because otherwise I cannot square root both sides because I want to make v the subject. M cancels out. I get v squared is equals to 2gm over r. And now I can square root v is equals to 2gm over r square root. So at this velocity, okay, this is escape velocity, the object will go away. Alright? That's another very important concept. Alright, so now we're going to be talking about moving in space. Okay? So when an object is moving like this in a circular motion, the object, okay, or let's say this is a satellite or a space station. This is a space station. Okay? Space station. Okay? So what's going to happen is usually astronauts are floating in space. And the reason for that is because this space station is actually in free fall. So it's kind of like falling down. But the reason it doesn't fall into Earth is because it's also having this circular motion, this velocity it has. Okay, and the velocity is acting in this direction, in this direction, in this direction, in this direction, right? And due to inertia, they're actually moving with these velocities, plus they're also having this free fall. And because of this, what happens is that the space station is going to be moving around the Earth. And inside of the space station, we have a person, and we have the space station itself. This is the space station, this is the person. The space station is also falling down in free fall, and the person is also falling down in free fall. Okay? And because of that, the person is able to float. Okay? Right. And then if you take the reading on the scale here, so we can say that the reading will be the normal force, and then we have the mg force acting, okay, which is the weight of the person. And then we can say ma is equals to mg minus n, okay, and then n is equals to mg minus ma, okay. So we can say this, and then since the person is in free fall, the a is just equals to g. So n is equals to mg minus mg, and n is equals to 0. Okay. So this is what we call, the name for this entire thing is called the apparent weightlessness of astronaut. Okay. I hope this is clear. I know I didn't take a lot of time to explain this, okay, because this is just for revision again. Okay, if you want to know more in detail, I recommend you watch the video. It's around like 10 minutes, okay, in the playlist, so you can watch it. This is just for revision. Alright, now last very important thing. This is outside of spec, okay, outside spec, but really, this comes up so much, and I don't know why they haven't kept it in the spec. It's there in Cambridge spec, so I do want to teach you this, okay. Now, this is called the synchronous satellites, and we're going to be looking at what this is, okay. So also the orbit of synchronous satellite is called geostationary orbit, okay. And basically for this type of orbit, the satellite that's moving around in geostationary orbit, it will always be above the equator, and it will always be above this Earth's surface, okay, or you can say it will always be at rest relative to Earth, okay. So I've just drawn a diagram up there. This is, I try to draw it to make you understand, okay. So this satellite will move from west to east, and the most important point is that this point is extremely important, these 2 points. The last point, it has an orbital time period equal to the Earth's rotational period, which means if the Earth moves 360 degree in 24 hours, right? So if the Earth moves 360 degree in 24 hours and it comes back in this position, right? So I'm going to put a dot here. I'm going to put a little bit of a dot. And this dot, it moves 360 degree and comes here in 24 hours, right? We agree with that? Earth moves 24 hours. The satellite also will move in 24 hours and complete its one cycle and come back here. That's what it means it's at rest. So always this satellite will be above you. It will always be above you, and that's a big advantage to us. We always want satellites above us. We don't want them to move here and there. So it's going to cause continuous transfer of data, and you can easily communicate with the satellite. And remember, it moves from west to east, okay? And it remains directly above the equator. Alright, so that's an important point. Alright, final thing. again, a little bit out of spec, but just for the sake of, for you to be familiar with these things and know these things, because they have asked a few questions based on context on this. Okay, they'll give you information and they want you to be able to deduce stuff out of that information, but I'm already giving you that information, okay? So the first one is geosynchronous orbit or geostationary orbit, and then we have polar orbit, okay? So we already saw geostationary orbit as well as the same thing again. Okay, these points are just a repetition of what we just saw. Now, polar orbits are actually much closer to Earth. They're at a lower altitude, so they can give you more detailed images, and their orbital time period is actually much shorter. So their orbital time period is around 100 minutes, whereas for geostationary orbits, they have an orbital time period of 24 hours, so much larger time period for geostationary orbits, okay? Okay, and the rest of the stuff I think you can read, just a bunch of more examples, okay? Just go through it, and we'll do some questions as well. So we have a question here. In the 17th century, Kepler proposed his law of harmonics for planetary motion. This law suggested that the ratio of the square of the orbital period t to the cube of the mean radius r has the same value for all the planets that orbit the sun. Mathematically, his law of harmonics can be written like that. Okay, and we've actually proved this before as well. Okay, and then it says the table shows data for Earth and Mars. Show that if for Earth and for Mars, k has a value of 3 times 10 to the raised power of minus 19 per second square per meter cube. Okay, so all you have to do is, t square is equals to k and r cube, and I can further simplify it. And if I want to find the value of k, I'm going to be doing k is equals to t squared by r cube. So I'm going to plug in the values there, and I'm going to see my answer. So I'm getting a value of 2.958 times 10 to the raised power of minus 19 second square per meter cube. Okay, now I'm going to do the same thing for Mars. And I want to plug in the values of Mars that they've given me up in the table. I'm going to get a very similar answer as well. And both values are actually approximately equals to the value that they have told us to show. Okay, so that's the answer to this question. Okay, the next part says Kepler's law of harmonics was derived later by Newton. Now, Newton applied his law of gravitation to a planet moving in an approximately circular orbit around the sun. Determine a value for k by applying Newton's law of gravitation to a planet of mass m moving in a circular orbit about the sun. And using Newton's method, we're supposed to find the value of k. Okay, so how will we go about this? So we're going to be applying Newton's law of gravitation, which is F is equals to gmm over r square. Okay, and it says to us, he applied this law of gravitation to a planet. So it's a planet, and this planet will be orbiting the sun. Okay, and we can apply the law of gravitation, which is F is equals to gmm over r square. And this planet is moving in circular motion. So I can say the gravitational force is equals to the centripetal force. So gmm over r square is equals to mr omega square, where the small mass is the mass of this and the big mass is the mass of the sun. So I'm going to cancel both m's out. I'm going to be moving the r down. I'm going to get r cubed, and then omega is 2 pi by t, and that's supposed to be squared, and that's supposed to give me 4 pi squared by t squared gm by r cubed. And then I'm going to move things around, and I'm going to get this as my value of k. So I'm going to plug in the value. So I've plugged in the values. They've given me the mass of the sun already. It's right up there, and now I'm going to get my answer. So I'm getting an answer of 2.97 times 10 to the raised power of 19, which is actually very similar, or actually the same as the answers we got above. Okay, so that's how we proved this. I've again shown this already, and in the videos as well. So now we're going to be going to part 3 of the question. So let's go through this. Jupiter is the most massive planet in the solar system and has many moons. Kepler's law of harmonics applies to the orbiting moons as well. However, the value of k for the moons is not the same as the value that applies to planets orbiting the sun. Makes sense? So Ganymede is Jupiter's largest moon, and Ganymede has an orbital radius of that, and it has an orbital period of that. Okay, that makes sense. Okay, let's highlight this. So orbital radius, and then we have an orbital period for Ganymede, and then we have another moon Io, and then it has an orbital radius of this. Okay, so first of all, I know t square is equals to k r cubed. Now what I'm supposed to find is the orbital period of TIO. Okay, so let's write the orbital period of G, which is Ganymede, square is equals to k, the orbital radius of Ganymede cubed, and the time period of IO square is equals to k r, the time period of I cubed. Okay, now if I make k the subject in both cases, I can see that these two time period divided by the orbital radius both will be equal, so I can equate both of them. So tg square is over rg square is equals to ti square over ri square. Okay, remember that right there is for Ganymede and that one is for Io, and when I plug in the values, this is what I get. So let's find the time period of Io square. What's that equal to? And remember, the time period of Ganymede is given to us in hours, so I've multiplied it by 3600 to change it into seconds. So this is going to be 2.35 times 10 to the raised power of 10, and the final value of the time period is 1.53 times 10 to the raised power of 5 seconds. That's going to be your answer. Also, this is cube. Okay, welcome back to another exam walkthrough. We have got here a question from basically it's kind of like a combination of oscillation plus gravitational fields. Okay, so we have a combination of both of these. I'm going to put it in the gravitational field playlist. Okay, so it says a simple pendulum has a time period of 2 seconds on Earth. Okay, and calculate what the period would be if the pendulum was on the planet Venus. Okay, so what do we have to do here is we have to see t is equals to 2 pi square root L over G. Okay, and what I need is the value of L here. So I'm going to plug in 2 is equals to 2 pi square root L over 9.81. And then I'm going to find the value for L. And the L value is going to be 0.9936 meters. Then I'm going to find the gravitational field for Venus. That's going to be G is equals to Gm over R square. And that's going to give me 8.874 Newton per kg. And now what I'm going to do is I'm going to find the new time period if the pendulum was on the planet Venus. So 2 pi square root 0.9936 over 8.8745. And that's going to give me the new time period as 2.1 seconds. Okay, we have an MCQ. It says the Earth has 10 times the mass of Mars and twice the radius of Mars. The gravitational field at Earth's surface is GE, and the gravitational field at Mars' surface is GM. So my aim here is to find GE over GM, because if I move this to the other side, okay, and if that doesn't work, then I'm going to be moving these to the other side, okay. So my aim is, first of all, I'm going to find this, okay, that's the first thing I'm going to do. And then I'm going to play around with this and move the values, and then I'll see what I get, okay. So the gravitational field at Earth is G times the mass of Earth and the distance, the radius of Earth square. And then we have the gravitational fields of Mars, which is G times the mass of Mars divided by the radius of Mars. Now the reason we are taking this as the radius is because we're considering the gravitational field strength at the surface of these planets. And I'm going to divide both the equations. And this is what things should be looking like. I'm going to cancel that g out. And further simplifying it, I get this. Okay, so this is the mass of Earth times the radius of the Mars square, the mass of Mars times the radius of Earth square. And we know from the start of the question that the mass of Earth is 10 times the mass of Mars, and the radius of Earth is twice the radius of Mars. So I'm going to plug those things in, and then this is what I'm going to get. So the mass of Earth has been replaced by 10 times the mass of Mars, and then the radius of Earth square has been replaced by 4 times the radius of Mars squared. The reason why it's 4 is because, remember, it's 2 times the radius of Mars, so when you square it, it becomes 4. Okay? I hope I wasn't too quick. So then you're going to cancel the values out, so they're going to get cancelled. These two are going to get cancelled, and you're going to get 10 by 4 is equals to GE over GM. So that's going to be GE is equals to 2.5 GM. And I could flip things around as well, so I could flip this up and this down, and this up and this down. And we would get GM over GE is equals to 4 by 10. So GM is equals to 0.4 GE. Now look, I told you at the start we were going to play around with it, and we could find the two things that we need. Now look up. If you compare, then our correct answer is A. Now we're going to be looking at this question, which is comparing the gravitational and electric fields. So electrostatic forces and gravitational forces can be both modeled by the idea of field. Give one similarity and one difference between electric fields and gravitational fields. Okay, so for the similarity, you can write both obey the inverse square law, both the fields, and here we have the equation as well, which shows that they obey the inverse square law. Now, if you want to know a little bit more in detail, or you want to know all the possible answers to this type of question, I definitely suggest that you go to the playlist video. In that playlist video, I've actually included most of the points that they ask about these type of questions. Okay, so yeah, so both obey the inverse square law. Now I will include a few more points here as well. So they both have infinite ranges. You can write that as well. You can write that both of them are radial. Both the fields are radial. You can also write they both are an example of action at a distance. Okay, so those things are you can write. Now for difference, you can write that the gravitational field are for masses. Let me just write it properly. So the difference you can write is gravitational fields exert gravitational force on masses, but electric fields exert electric force on charges. You can also write other points such as that electric forces that act on charges are way stronger than the gravitational forces, given that they have the same separation. The charges and masses, they have the same separation. You can also write that gravitational fields are always attractive. Okay, and you can also write that the electric field can be attractive or it can be repulsive as well. So these are pretty much all of the type of answers that you can write. You can also write that the gravitational potential is always negative, and you can also write that the electric potential, it can be positive or it can be negative. So these are all the type of points that you can write. I prefer writing these two. This is for 2 marks. Let's move. Here we have another question. The graph shows how the gravitational field strength G of the Earth varies with distance r from the center of the Earth. And they've given you the values here. So they've given you the gravitational field on the y-axis, and then on the x-axis they have given you r, but in terms of the radius of Earth. So r is given in multiples of the radius of the Earth. Okay, so it's like 1 RE means 1 times the radius of Earth, 2 RE means 2 times the radius of Earth, and then so on it goes until 7. And then you have to show that G obeys the inverse square law. So we know the formula of gravitational field strength is going to be G is equals to Gm over R squared, where G is the gravitational field strength and R is the separation or the distance from the center of one mass to the center of the other. So everything G is equals to K over R squared. So all you have to do is you have to do g times r squared is equals to k. And if you can show that for both things, that gives you a constant, which means that it obeys the inverse square law. So I'm going to pick two values out here. So let's pick this right over here, which is 1 RE, and that's going to be 9.8. Okay, this is the value 9.8. So I'm going to pick 9.8 RE squared. Okay, and then let's pick another value from here. Let's pick 4 here. And then let's take this right over here. And we should get 0.6. Okay, so that's going to be equals to k. And then for the other point we selected, it was 0.6 times 4, was it 4 RE? Yeah, 4 RE squared. Okay, I think we did that, yeah, okay. And that's supposed to give me 16 RE squared, because 4 times 4 is 16. And when I multiply this two values, I'm going to get 9.6 RE squared, which is equals to k. So k is approximately same in both cases. 9.8 RE squared is approximately same as 9.6 RE squared. So k is equals to k. Both k is constant, so k is constant, and hence it obeys the inverse square law. A satellite is launched from the surface of Earth into an orbit height of 5 RE above the surface of the Earth. The change in gravitational potential energy of a mass when it experiences a vertical displacement can be calculated using this equation. Now we have to explain why this expression cannot be used to calculate the change in gravitational potential energy. Well, that's quite simple. It's because g is not constant, it's changing. When we use this equation, I've explained it, that g, we assume it to be 9.81 constant, but it isn't actually constant, so we can't use this, okay? Okay, now we have the final part, which says calculate the change in gravitational potential energy of the satellite. So let's do this now. So we have the mass of Earth here, and the satellite goes from the surface of Earth to here, and it's going to be at a distance of 5 RE, and this give me a second, and this distance here is RE. So it goes from RE to 5 RE. Okay, and now what we have to do is, we know the change in GPE is equals to M and then change in V. Okay, and then I know that the change in V is equals to the final position, the final potential minus the initial potential, and that's going to be GM minus GM over 5 RE minus GM RE. Okay, right. Then we can further simplify this: minus GM over 5 RE plus GM over RE. Make sense? I'm going to take that GM out, so GM minus 1 over RE, 5 RE, plus 1 over RE. Okay? Then I'm going to take this, and I'm going to put it up there, paste. I'm going to move it right over here. Okay? And then this is supposed to be multiplied with M. Okay, this is the capital M, mass of the Earth, and this is the small m, mass of the satellite. So this is the mass of the satellite, mass of the Earth. Make sense? Now I'm going to put this right over here, multiplied. So GME MS minus 1 over 5 RE plus 1 over RE. Now all you have left is to just plug in the values and you will get the answer. And you're going to get the answer as 1.75 times 10 to the raised power of 11 joules.